Alright guys, welcome back to Underground Science, and in this video we'll be talking about paramagnetic elements, right, or paramagnetism. And so hopefully you guys just came back from my diamagnetism video where I talked about two examples of diamagnetic elements, and in this video we'll talk about two examples of paramagnetic elements. Alright, so the two examples that we're just going to choose is, let's do scandium, and let's do one from here, let's do aluminum. Alright, so let's go and show these two examples and see how these two examples are paramagnetic and what that means. Alright, so pretty much before we start, just know that the way to identify paramagnetic elements is to see if they have any unpaired electrons in their energy level or in their last energy level. Alright, so let's go and write that down, in last energy level. Alright, so that's how you see if an element is paramagnetic or and then if you want to see if the element is diamagnetic, like we said in the last video, if it's diamagnetic, it has no unpaired electrons. But in this video, we're talking about paramagnetism, right? So just look for unpaired electrons in the last energy level. Forgot that word. All right, so let's go and get started. So first step, as always, like we said in the last video in diamagnetism, is that make sure to write the electron configuration notation first. So we're going to start with 1s2, then we're going to move on to the second energy level, and we have a p orbital also that has three different orientations, so 2p6, 3s2, and remember, I don't know why, but let's just do scandium first. All right, so let's do 3p6, and then 4s2, then we have to make sure to be careful and write our 3d1, all right, because the d orbital starts with our third energy level, even though it may look like we're supposed to write 4d1 because we're in our fourth energy level, it starts in our third energy level, all right, for our d orbital, our transition metals. All right, so let's go ahead and now draw this as our electron configuration or orbital diagram. So that's that, and so let's go and label these as just a whole, right, to save time. So 1s, 2s, then this whole thing is our 2p, but we know it's 2p. We have three different orientations, right? So 2px, so 2py, 2pz. And then we have our 3s here, and then we have our 3p as a whole, okay? So 4s here. Now, just the last step is to start plugging those electrons in, all right? So let's put our electrons in our 1s orbital. So we go here, all right? There's two electrons there. So let's go and write our positive 1/2 spin, negative 1/2 spin, done, right? 2s orbital, we can only fit two electrons. So positive 1/2 spin, negative 1/2 spin, all right? And then our 2p orbital, we can fit 6 electrons. So Hund's rule, right? And then, sorry about that. I'm going to erase this dot. All right, we have Hund's rule there, and then once we're done filling electrons in each subshell, because electrons repel each other, so we have to follow Hund's rule, then we go and add it back in. So 4, 5, 6. All right, sorry about these random dots. Okay, so our 3s orbital can fit 2 electrons, so positive 1/2, negative 1/2. 3p orbital, 6 again, so 1, 2, 3. Hund's rule, 4, 5, 6. All right, and 3d orbital has only it has an unpaired electron, all right, because it's not paired with a negative spin. It's not paired with a negative spin electron. It doesn't have that. So that means that scandium will be paramagnetic, all right, because technically when we're first writing electron configurations, right, we come across our s orbital first, and then we start our d block afterwards. So technically, we have to look at 3D this time, right, instead of 4s. Even though 4s has a no unpaired electrons, we still have to look at our 3D because that's what comes after our 4s, right? Like in terms of energy level, right, 4 is a higher energy level than 3, but right here we can see that the D block comes after the S block right here. This whole thing's the D block, so we have to consider the 3D orbital, and we do, right? So the 3D orbital for scandium has an unpaired electron, which is right here, right in the first D orientation, in the first D subshell. So that's why we identify scandium as paramagnetic, because it has an unpaired electron, right? So paramagnetic. And remember, or not remember, I haven't stated it yet, I don't think, but paramagnetic elements, unlike diamagnetic elements, paramagnetic elements are strongly attracted, are strongly attracted to an external magnetic field. All right, to an external, I'm sorry about that again, to an external magnetic field. Let me go and write this down here. All right, so let's go scroll down. So paramagnetic elements are strongly attracted to an external magnetic field. Remember, this is unlike our diamagnetic elements that we talked about in our previous video. In diamagnetism, our elements that are diamagnetic are not very attracted to an external magnetic field, all right? So that's what's different. And what's different is we have an unpaired electron when we talk about paramagnetism. Rather than diamagnetism, we don't have any unpaired electrons, right? So let's go ahead and look at another example that we said. Let's see what we say, aluminum. All right, so let's go and look at aluminum. You know what, let's just go and do this on a separate page, or let me just clear this page up real quick. So we got scandium down. Hopefully that made sense to you guys. Let's go and do aluminum. All right, so let's go and re-say what we're doing. All right, aluminum, and first step again, let's go and write out our electron configuration notation. It'll help us later, all right? So 1s2, 2s2, 2p6, 3s2, and 3p1. All right, and we have reached aluminum. All right, so the next step is to draw the electron configuration or orbital diagram. Okay, so let's go and write out the draw out the energy levels first. So 1s, 2s, 2p, 3s, and 3p. All right, so let's go and label that 1s, 2s, 2p. All right, let's just go and label it just cause. So 2pz, and then we have our 3s guys, and then our 3px, 3py, and 3pz. Okay, so now our last step. So our 1s orbital can hold 2 electrons, so positive 1/2, negative 1/2 spin. Quantum number 2s can hold 2 electrons, right? And then our 2p orbital can hold a total of 6 electrons because there's 3 different subshells, and each subshell can hold 2 electrons. So we follow the Hund's rule. So 1, 2, 3, then 4, 5, 6. Let me go and write that a little neater. Sorry about that. 4, we're at 5 and 6, all right? So, and then our 3s orbital, so we're done here, our 3s orbital can hold 2 electrons, so positive 1/2, negative 1/2 spin quantum number. And for aluminum, our 3p orbital only has 1 electron, so we write it as a positive 1/2 spin. Okay, so we look here and we see that we have an unpaired electron again in our 3px orientation of aluminum. So what that means, guys, is that since we have an unpaired electron, we're going to say that aluminum is paramagnetic. All right, so it's just that. All you have to look at is if either your last energy level or your next orbital section, right? So as we saw in scandium, or d orbital section, if one of those two, if we have an unpaired electron, right? If we have no unpaired electrons, we were talking about diamagnetic. But if we have an unpaired electron, like we just saw in aluminum and in our previous example, scandium, then we're talking paramagnetic. All right, and remember what paramagnetic means is that we have our element is going to be strongly attracted to a magnetic field. All right, so strongly attracted to an external magnetic field. All right, so that's it, to an external magnet. So if you put a magnet here near aluminum, we're going to get some attraction. All right, so external magnetic field. And that's it, guys. That's paramagnetism, right? So just remember 2 things. In terms of actually deciding if it is, remember first write the electron configuration notation to help you draw the orbital or electron configuration diagram. And then just look at if you have any unpaired electrons, right, in your last orbital that you have or your last energy level. And if you do have an unpaired electron, then we have paramagnetic, or we're working with a paramagnetic element. And if we don't have any unpaired electrons, as we saw in our previous video, like in magnesium or in beryllium, then we're working with a diamagnetic element. All right, so that's pretty much it for paramagnetism. I hope this video made sense to you guys. I hope to see you guys in my future videos. We'll talk about more cool topics in biochem, physics, and chem. And so see you guys later, and make sure to stay safe.